We already established that the electric field at any point in insulating materials is determined by averaging the microscopic electric field E sub m over a small volume enclosing that point, which is the superposition of the electric fields E sub E and E sub B due to the extraneous or free charges and the bound charges in the dielectric medium. Since these electric fields are microscopic in nature, we use their averages over very small volumes to describe the macroscopic electric field in dielectrics. However, if we want to determine the local electric field strength acting on an arbitrary molecule inside the dielectric, it is not longer enough to calculate the effect of these macroscopic fields on that molecule. In general, the local field strength at an arbitrary point in the dielectric, for example at the location of a molecule, is determined by the field E naught due to external sources and the field strength of the molecules in the dielectric with dipole moment. In order to determine the electric field due to polarized molecules in an insulating material, Hendrik Lorentz, the famous Dutch physicist, applied a method using the so-called Lorentz cavity or Lorentz sphere to calculate the local field acting on a molecule by separating local dipoles from distant ones. In this method we consider an imaginary sphere around an arbitrary molecule in a dielectric medium under the influence of a uniform electric field E naught, whose radius r should be small enough compared with the physical dimensions L of the polarized dielectric, but large enough compared with the distances d between the molecules in the medium. Then the electric field acting on the molecule in the center of the Lorentz sphere that is due to the polarized molecules outside the cavity can be considered as the superposition of two different fields. The electric field E' due to the polarization charges over the outer boundary surface of the dielectric material, and the electric field E1 due to the polarization charges over the boundary interface between the Lorentz sphere and the dielectric medium excluding the molecules inside the cavity. The effect of the molecules inside the sphere on the molecule at the center of the sphere is described by the electric field E2 depending on the atomic structure of the dielectric inside the cavity. As a result, the electric fields E1 and E2 has local contributions to the effects of the electric field strengths E naught and E' on the molecule. Now we determine these contributions for specific type dielectric materials in the case of uniform polarization. We start with the electric field E1 due to the polarization charges over the boundary surface of the Lorentz cavity, where the polarization surface charge density sigma prime at any point of the boundary surface of the cavity can be written as the dot product of the polarization P of the dielectric surrounding the cavity and the inward pointing surface normal n at the point. In this case the normal vector points outward from the insulating material surrounding the cavity. If the dielectric medium is homogeneous and isotropic, then the polarization P produced by the uniform electric field E naught is uniform as well. Therefore, the vector field P has a fixed direction, and we can introduce the angle theta between the unit normal n at any point on the cavity surface and the direction of the polarization field P. Then the polarization surface charge density sigma prime is given by the magnitude of the polarization field P times the cosine of the angle theta. Now we calculate the electric field due to this surface charge distribution over the Lorentz sphere at the center of the sphere. The magnitude of an infinitesimal field dE at the center of the sphere produced by the infinitesimal amount of polarization charge dq' at any point on the sphere is equal to 1 over pi times the vacuum permittivity epsilon naught, times the charge dq' over the square of the radius r of sphere. The infinitesimal polarization charge can be written as the polarization charge density sigma prime, times the surface element ds at the given point on the sphere, where sigma prime is equal to the magnitude of the polarization P times cosine theta. We need to integrate this quantity over the whole surface of the cavity to determine the net electric field due to the total amount of polarization charges over the surface of the cavity. However, the component of the electric field perpendicular to the polarization field vanishes for such an integration over the sphere in a uniform polarization field. Hence, we only consider the tangential component of the field strength due to each charge element, which is given by the magnitude of the electric field dE times cosine theta. Then we can express the infinitesimal field dE1 as 1 over pi times epsilon naught, times the ratio of the magnitude of the polarization P to the square of the radius r of sphere, times the square of cosine theta, times the surface element ds. Now we integrate the infinitesimal element of the field strength over the surface of the Lorentz sphere to obtain the electric field E1 at the center of the sphere, and substitute the expression obtained for dE1 into the integral. Here the surface element ds can be written as the square of the radius r of the sphere, times the sine of the angle theta times the differential of the angle theta, times the differential of the azimuthal angle phi in the spherical coordinate system attached to the center of the sphere such that the polar axis of the coordinate system is parallel with the polarization field P. As a result, the magnitude of the electric field E1 is equal to P over 4 pi times epsilon naught, times the double integral of the square of cosine theta times sine theta with respect to the polar angle theta and the azimuthal angle phi, where the boundaries of integration cover the whole Lorentz sphere. Since the integrand does not depend on the angle phi, the integral with respect to phi from 0 to 2 pi gives 2 pi, and we can reduce the right-hand side to p over 2 times epsilon naught, times the integral of the square of cosine theta times sine theta with respect to theta from 0 to pi. By introducing the variable x for cosine theta, we can write dx as minus sine theta times d theta, and transform the integral to the negative integral of x squared with respect to x from plus 1 to minus 1. The primitive function of this integral is x cubed over 3, and its evaluation on the limits gives 2 over 3. Then the magnitude of the electric field strength E1 due to the polarization charges over the surface of the Lorentz cavity is equal to the magnitude of the polarization P over 3 times the vacuum permittivity epsilon naught. In the second step we determine the electric field E2 due to the dipole molecules within the Lorentz cavity that act on the molecule at the center of the cavity. We suppose that the dielectric material is homogeneous and isotropic, that is, the molecules inside the medium has the same dipole momentum in a uniform electric field pointing in the same direction. Now we also assume that these molecules are ordered in a cubic crystal lattice, since this symmetry helps us to reduce the complexity of the problem in a great extent. When we studied electric dipoles, we determined the electric field due to the system of electric dipoles at a given point where the position of the ith electric dipole is described by the position vector Ri pointing from the given point to the dipole. Here all the molecules have the same dipole moment p, and we can write the electric field as the sum of the difference between 3 times the dot product of the dipole moment p and the position vector Ri of the ith molecule times the position vector Ri, and the square of the length of Ri times the dipole moment p, over the length of Ri raised to the 5th power, where the index I runs through all the molecules inside the cavity expect the one at the center. If we attach a Cartesian coordinate system to the center such that its z-axis points to the direction of the polarization field P that is of the axes of the dipoles, then the electric field E2 due to the polarized molecules has only a non-vanishing z component. Consequently, it is enough to calculate the z component of the field strength, where the dot product has only one term for the product of the dipole moment p and the coordinate zi, and the z component of the dipole moment p is simply the magnitude of the dipole moment p. Then the magnitude of the dipole moment p can be factored out from the sum, and the square of the length of the position vector Ri can be written as the sum of xi squared, yi squared, and zi squared. If we consider the symmetry of the cubic lattice structure of the dipoles and the symmetric arrangement of the Lorentz sphere, then the directions along the Cartesian axes are equivalent, and the sum of square of the x, y, and z coordinates over the length of the position vector Ri to the 5th power are equal to each other for the complete sum of the molecules within the sphere. As a result, xi squared and yi squared can be replaced by zi squared in the fraction, and the total sum gives 0, stating that the contribution of the polarized molecules within the Lorentz cavity to the local electric field at the center vanishes in a medium where the molecules are arranged in a cubic crystal lattice. It can be shown that this field also vanishes in isotropic materials and in any media with a random distribution of molecules. The resultant microscopic electric field E sub m is the local field acting on a molecule in any insulating material, usually denoted by E log. Whereas the net external electric field E acting on a given molecule is the superposition of the external field E naught and the electric field E prime due to the polarization charges over the outer boundary surface of the dielectric medium. Then the local electric field E log in any dielectrics can be written as the sum of the net external field E acting at a given point in a material, and the polarization vector field P over 3 times the vacuum permittivity epsilon naught. This resultant field is called the Lorentz field in homogeneous and isotropic dielectric media. We already saw that the polarization field in a dielectrics is approximated by the volume average sum of the electric dipole moments of the molecules. We also assumed that the polarization field can be expressed in terms of electric susceptibility of the dielectric and the electric field strength polarizing the dielectric in a linear form for a homogeneous and isotropic insulating material. Then we can introduce a similar expression for a single molecule in such materials, and we can define the polarizability of one atom or molecule such that the dipole moment p of the atom or the molecule is given by the molecular polarizability alpha, times the local electric field strength E log acting on the atom or the molecule. Since the SI unit of the dipole moment is Coulomb times meter and the SI unit of the electric field strength is volt per meter, the SI unit of the molecular polarizability is Coulomb times square meter per volt. Then polarizability is the measure of how easily an electron cloud or the charge distribution in an atom or a molecule can be distorted by an external electric field, creating an induced dipole moment. It represents the ability of a material to form dipoles, which determines the total dielectric polarization of the medium. The anisotropic version of molecular polarizability is its generalized form called molecular polarizability tensor, which is a symmetric second-rank tensor mapping the vector field of the local electric field strength at any point within the dielectric to the electric dipole moment of a molecule at that point due to polarization. That is, the dipole moment P of the molecule is given by the contraction of the molecular polarizability tensor alpha of the dielectric with the local electric field E loc acting on the molecule. In a Cartesian coordinate system attached to the molecule at the given point, the I components of the dipole momentum P of the molecule is equal to the sum of the components alpha sub ij of the molecular polarizability tensor, times the j component of the local electric field E loc for the indices I and j denoting the Cartesian indices x, y, and z. This equation shows that the local electric field often causes the induced dipole to differ in direction from the field, and in many cases we can diagonalize the matrix representing the polarizability tensor in a principal axis system determined by the symmetries of the molecular structure of the dielectric. Then the molecular polarizability of the insulating material can be represented by the three principal values of the polarizability tensor. In fact, the total polarization of a material is usually the sum of three main mechanisms based on charge displacement: electronic displacement or electronic polarization, ionic displacement or ionic polarization, and orientation displacement or orientation polarization. When we classified dielectrics into the groups of nonpolar dielectrics and polar dielectrics, we explained how electric dipole moments are induced by the shift of opposite charges in an atom or a molecule in the opposite directions. Electronic polarization is the process by which an atom's electron cloud is distorted under the influence of an external electric field. When an electric field is applied, the negatively charged electron shifts slightly opposite to the field, while the positively charged nucleus shifts in the direction of the field, but this shift is very little due to its much larger mass. This separation of charge creates an induced electric dipole moment within the atom. The process of electron cloud deformation is independent of temperature and happens rapidly in the order of 10 to -14 or -15 seconds. The magnitude of this induced dipole is proportional to the applied field and is characterized by the electronic polarizability. Ionic polarization occurs in materials like ionic crystals, where positive and negative ions are arranged in a regular lattice structure. When an electric field is applied, positive ions shift slightly in the direction of the field while negative ions move in the opposite direction, creating many induced dipoles. This collective displacement produces a strong overall polarization in the crystal. Unlike electronic polarization, ionic polarization involves the movement of entire ions, making it slower due to their larger mass and the restoring forces of the lattice. This mechanism, characterized by the ionic polarizability, only exists in materials with distinct charged ions, and it is absent in covalent solids where such ion displacement cannot occur. These two types of displacement polarization occur only in materials with nonpolar molecules, where the molecules polarized in an electric field behave as elastic dipoles held together at their ends of opposite charges by elastic forces. Orientational polarization occurs in materials made of polar molecules which possess permanent electric dipole moments. When an electric field is applied on these dipoles that are randomly oriented due to thermal motion resulting in no net polarization, it exerts a torque on the dipoles attempting to align them with the field direction. Although complete alignment is not achieved, a partial average alignment produces a net polarization. This mechanism differs from electronic and ionic polarization because it does not create dipoles but reorients existing ones. The process is strongly influenced by the competition between the aligning effect of the electric field and the randomizing effect of thermal energy. As temperature increases, thermal motion dominates and reduces the degree of alignment. Consequently, orientational polarization decreases with increasing temperature, typically varying inversely with temperature. In some cases, such as in solid ice, molecular rotation is restricted, preventing dipole alignment and effectively eliminating orientational polarization. The total polarizability of a dielectric medium is the sum of these contributions determined by the molecular structure of the matter, that is the sum of the scalars or the tensors representing each type of molecular polarizability. As already mentioned, we approximated the polarization field in a dielectric material as the average sum of the electric dipole moments of the molecules over a small volume enclosing some molecules. Instead of averaging over the volume, we can also express the polarization vector in terms of the concentration of atoms or molecules, that is their number density measured in the number of atoms or molecules per unit volume. Then the polarization P in an insulating material composed of a mixture of different types of atoms or molecules, is equal to the sum of the atomic or molecular concentration Ni of the atoms or the molecules of the type I, times the electric dipole moment Pi of the atoms or molecules of the type I, where the index I runs through all the n different types of atoms or molecules in the material. If the substance contains only one type of atoms or molecules, then the polarization field P at the position of an atom or a molecule is given by the number density n of the atoms or the molecules in the medium, times the electric dipole moment P of the atoms or molecules. For the sake of simplicity, we consider atoms as monatomic molecules and we will only talk about dielectric materials composed of molecules. The polarization field can also be written as the molecular concentration N times the molecular polarizability alpha of the molecules, times the local electric field E loc acting on the molecules. The equations of polarization expressed in terms of molecular concentration are very convenient in the study of the polarization of gases, since they help us to determine the relationship between the electric susceptibility or the dielectric constant and the molecular polarizability for gases. Because the average distances between the molecules are relatively large in dilute gases, the difference between the local and macroscopic field strengths given by the superposition of the internal electric fields E1 and E2 can be neglected for both polar and nonpolar gases. Hence, the macroscopic electric field E is a good approximation for the local electric field E loc, and we will use this approximation for both polar and nonpolar gases at low pressure. For gases composed of nonpolar molecules, such as noble gases like helium, neon, and argon, or diatomic gases like hydrogen, oxygen, and nitrogen, the polarization P of the gaseous substance can be written as the atomic or molecular concentration N, times the molecular polarizability alpha of the molecules, times the electric field strength E. Now we compare this equation with the one stating that the polarization vector P is equal to the electric susceptibility chi E of the gaseous substance, times the vacuum permittivity epsilon naught, times the electric field strength E. Then we conclude that the electric susceptibility chi E given by the relative dielectric constant epsilon R of the gas minus 1, is equal to the product of the number density N of the molecules and the molecular susceptibility alpha of the gas, over the vacuum permittivity epsilon naught. In the case of gases composed of polar molecules like carbon monoxide, ammonia or hydrogen chloride, we must take the effect into account that attempts to change the orientation of the molecules with a permanent dipole moment in an external electric field align them with the field. As already mentioned, the dipoles in any substance composed of polar molecules are randomly oriented due to thermal motion. The torque produced by the electric field aligns the dipoles in the direction of the field, minimizing their potential energy. However, the thermal excitation of the polar molecules tends to disrupt this alignment, acting against the torque produced by the electric field. Due to the net effect of the competition between the thermal motion and the torque, the randomness of the orientation of the dipoles can only be reduced but cannot be eliminated completely. This fact must be taken into account when the polarization of the gas is determined by averaging the electric dipole moments of the polar molecules under the influence of an external electric field. When we studied electric dipoles, we found that the potential energy U of a dipole in a uniform electric field E is given by the negative projection of the dipole moment P of the dipole onto the electric field strength E. Then U can be written as the negative product of the magnitudes of the dipole moment P and the field strength E, times the cosine of the angle phi between the direction of the axis of the dipole and the electric field. For the polarized molecules of a polar gas, the magnitude of the permanent dipole moment P is constant, whereas the orientation angle phi of the dipole is a random variable that have a value between 0 and 360 degrees. However, only the component of the dipole moment along the field contributes to the polarization, which is given by the constant magnitude of the dipole moment P times cosine phi. Then it is enough to compute the average of cosine phi in this product, and we consider cosine phi as a random variable x covering the range between -1 and 1. If we want to calculate the average value of a discrete random variable x, we need to calculate the sum of the products of each possible outcome and its corresponding probability. Here the statistical weight Wi describes the probability of the outcome xi for the variable x, and the average of x can be written as the sum of the weight Wi times the value xi of the variable x for the index I running through all the possible n outcomes. This sum is divided by the sum of the weight Wi from I equals 1 to n to provide a normalization for the statistical weights. For example, in the case of a standard 6-side dice, the random variable is the different outcomes of its rolling described by the integers from 1 to 6, and its statistical weight must be the same for each outcome. With the normalization, their values are given by 1 over 6, and the average of the random variable x is equal to 3.5 for the outcome of rolling the dice. Because the random variable x given by the cosine of the orientation angle phi of a dipole is a continuous one, the statistical average written in terms of sums must be generalized to an expression written in terms of integrals. Then the average of x is given by as the integral of the statistical weight w as a function of x times the random variable x with respect to x, divided by the integral of the statistical weight w with respect to x. The upper and lower limits of the integrals must cover all the possible values of the random variable x, which is the interval between -1 and 1 in this case. In statistical mechanics it can be shown that the statistical weight w for gas molecules in thermal equilibrium is described by the Boltzmann distribution function, that is the weight w is proportional to the exponential function of minus the potential energy U of the gas divided by the product of the Boltzmann constant K and the absolute temperature T of the gas. For one dipole in a given statistical state defined by its orientation, we can substitute the explicit form of the potential energy U of the dipole into this expression, and write the right-hand side as the exponential of a ratio of p times e times cosine phi to k times t. Here cosine phi can be written as the random variable x, and by introducing the parameter a for the ratio of p times e to k times t, we can state that the statistical weight w is proportional to the exponential of ax. Then the integral of the statistical weight w with respect to the random variable x is proportional to the integral of the exponential of ax with respect to x from -1 to 1. The primitive function of the integrand is equal to e to ax over a, which can be evaluated at the lower and upper limits. As a result, we obtain the exponential of -a over a, minus exponential a over a, that is -2 times sin a over a. The integral of w times x with respect to x is proportional to the integral of the exponential of ax times x with respect to x from -1 to 1. When integrating this expression by parts, we evaluate the exponential of ax times x over a at the limits -1 and 1, and subtract 1 over a times the integral of exponential of ax with respect to x from -1 to 1. This gives the negative exponential of minus a over a, plus exponential a over a, plus 2 times sin a over a squared. Then the result can be written as -2 times cos a over a, plus 2 times sin a over a squared. If we substitute the expressions derived for the two integrals into the formula for the averaging of the continuous random variable x given by cosine phi, the proportionality factor of the statistical weight emitted here cancels out in the numerator and the denominator of the fraction. After simplifying the fraction with -2 times sin a over a, we obtain coth a minus 1 over a. The left-hand side of this equation is called the Langevin function L with the argument a, which is used to describe the alignment of both electric and magnetic dipoles in a polar dielectric or a paramagnetic material under an applied electric or magnetic field. This result can be substituted into the averaged permanent electric dipole moment of polar molecules of a gas under the influence of an external electric field, which provides a contribution to the polarization field in the gas given by the magnitude of the permanent dipole moment P of the gas molecules, times the Langevin function L evaluated at the product of the magnitudes of the dipole moment P and the external electric field E over the product of the Boltzmann constant K and the gas temperature T. In the relevant cases the electric field E applied to the gas is weak and the temperature T of the gas is high. Then the ratio of P times E to K times T is much smaller than 1. And the Langevin function of the variable x can be approximated by x over 3. Consequently, the average permanent dipole moment P of the gas molecules in the external electric field E can be written as the square of the magnitude P of the dipole moment over the product of 3 times the Boltzmann constant K and the gas temperature T, times the field strength E. Although the dipoles are not perfectly aligned with the field, their average can be approximated in this way for weak fields and high temperatures. Since the polarization in a polar gas is due to both the electron polarization of the gas molecules and the orientation polarization of their dipole moments, we can write the polarization capital P as the number density n of the molecules, times the sum of the induced polarization and the averaged permanent dipole moments in the gas. Here the sum can be written as the sum of the molecular polarization alpha of the gas times the electric field strength E, and the ratio of P squared over 3 times K times T, times the vector E. Then the polarization is given by n times the sum of alpha and the ratio of P squared to 3 times K times T, times the field strength E. As already seen, the polarization vector capital P is also equal to the vacuum permittivity epsilon naught, times the electric susceptibility chi E of the gaseous substance, times the field strength E, where chi E is given by the relative permittivity epsilon R of the gas minus 1. If we compare these two expressions describing the polarization, then we conclude that the electric susceptibility chi E of the gas or its relative permittivity epsilon R minus 1, can be written as the concentration N of the gas molecules over the vacuum permittivity epsilon naught, times the sum of the molecular polarizability alpha of the gas and the square of the magnitude of the electric dipole moment P of the molecules over 3 times the Boltzmann constant K, times the temperature T of the gas. By comparing this result with the corresponding formula obtained for nonpolar gases, we can recognize the first term in the parentheses describing the electron polarization of the gas, which is present in the case of both nonpolar and polar gases. Here the second term in the parentheses is the contribution from the orientation polarization of the molecules with permanent electric dipole moments in polar gases. We can provide a more accurate description of the polarization of nonpolar gases if we do not neglect the Lorentz field induced in the gas when an electric field E is applied on its molecules. Then the polarization field P given by the number density N of the gas times the induced dipole moments of the molecules is equal to the concentration N times the molecular polarizability alpha of the gas, times the sum of the electric field strength E and the polarization vector P over 3 times the vacuum permittivity epsilon naught. If we solve this equation for the vector P, we can write the polarization as N times alpha, times the reciprocal of 1 minus N times alpha over 3 times epsilon naught, times the vector E. Now we compare this equation with the one seen above where P is expressed by epsilon naught, times epsilon or minus 1, times E, and we state that N times alpha times the reciprocal of 1 minus N times alpha over 3 times epsilon naught, is equal to epsilon naught, times epsilon or minus 1. By introducing the shorthand notation B for N times alpha over 3 times epsilon naught, we can write this equation in a simple form, stating that 3 times B over 1 minus B is equal to epsilon or minus 1. If we multiply this equation by 1 minus B, then its right-hand side becomes epsilon or minus 1, minus epsilon or times B plus B. After simplifying this equation, we can write that the product of epsilon or plus 2 and B is equal to epsilon or minus 1. Finally, we divide this equation by epsilon or plus 2 and substitute the original expression into B. As a result, we obtain the Clausius-Mossotti equation stating that the relative permittivity epsilon R of a nonpolar gas minus 1 over epsilon R plus 2, is given by the number density N of the gas molecules times the molecular polarizability alpha of the gas over 3 times the vacuum permittivity epsilon naught. The equation was named after two scientists. The first one is Rudolf Clausius, one of the founders of thermodynamics, who in his study on the interaction of electric fields with matter introduced ideas about how individual molecules contribute to polarization, and recognized that the field acting on a molecule differs from the externally applied field. The second one is Ottaviano Fabrizio Mossotti, who determined a relation between the dielectric constant of a material and the properties of its constituent particles while he worked on dielectric materials and drew analogies between electrostatics and elasticity. Their contributions are manifested in the Clausius-Mossotti equation, providing the first important connection between microscopic properties of matter like molecular polarizability, and its macroscopic properties like dielectric constant. We have the following remarks on the Clausius-Mossotti equation. For dielectrics belonging to the group of nonpolar and weakly polar fluids such as vegetable and mineral oils, benzene, and toluene, which have small relative dielectric constants between 2 and 2.5, electronic polarization is the dominant effect. In this case, the Clausius-Mossotti equation adequately describes the relationship between the polarizability and the dielectric constant of such fluids. In polar liquids there are usually very strong electric fields due to the interaction of polar molecules located close to each other. The Clausius-Mossotti equation is no longer applicable here, and other theoretical models serve to describe the relationship between the microscopic and macroscopic properties of the fluids that is in a good agreement with the experimental data. If the only dominant mechanism in the polarization of a solid dielectric is electronic polarization and its relative permittivity is small, then the Clausius-Mossotti formula is valid for the given insulating material. Since the internal electric field in ionic crystals with a cubic structure is described by the Lorentz field, the Clausius-Mossotti equation can be applied in this case as well. In general, determining the relationship between polarizability and dielectric constant is not an easy task. If we consider gases composed of polar molecules where the Lorentz field is taken into account, then the polarization field P given by the number density N of the gas molecules times the sum of their induced dipole moment and the average of their permanent dipole moment, is equal to the concentration N times the sum of the molecular polarizability alpha of the gas molecules and the square of the magnitude of the permanent dipole moment P over 3 times the Boltzmann constant K times the temperature T of the gas, times the vector sum of the external electric field strength E and the polarization vector P over 3 times the vacuum permittivity epsilon naught. In this case, we need to modify the Clausius-Mossotti equation by replacing the molecular polarizability alpha with the sum of alpha and the ratio of p squared to 3 times k times t. This formula is called Clausius-Mossotti-Debye equation, since the physicist and chemist Peter Debye introduced the concept of orientation polarization and determined its explicit form based on the statistical mechanical calculations presented here before. Hence, this equation describes not only electronic polarization due to the electron shell deformation in molecules but also orientation polarization due to the alignment of their permanent dipole moment. It is useful to define the molar polarization Pm of any substance by the ratio of its relative dielectric constant epsilon r-1 to epsilon r+2, times the molar mass m of the substance over its density ρ. As its SI unit given by cubic meter per mole shows, this quantity measures the total electric polarization produced in 1 mole of a substance when placed in an external electric field. In the case of gases, the number density n of the gas molecules is equal to the Avogadro's number Na times the density ρ over the molar mass m. If we substitute this expression into the Clausius-Mossotti-Debye equation, we can see that the ratio of epsilon r-1 to epsilon r+2, times m over ρ, is given by Na over 3 times epsilon naught, times the sum of alpha and p squared over 3 times k times t. Because we have the molar polarization Pm in the left-hand side of the equation, we can express Pm as a constant A, plus the ratio of another constant B to the temperature T of the gas. Here the constant A contains only the molecular polarizability alpha characterizing the physical properties of the gas molecules, whereas the constant B contains only the permanent dipole moment P of the molecules. Then, the molar polarization Pm written in this form reinstates the fact that polarizability is due to two mechanisms: electronic polarizability, which is independent of the temperature of the medium, and orientation polarizability, which depends on the temperature. One of the experimental methods for determining the permanent dipole momentum and molar polarizability is based on the Clausius-Mossotti-Debye equation expressed in terms of molar polarization. For example, if we measure the relative dielectric constant epsilon r and the density ρ of a gas at different temperatures T, then we can compute the molar polarization Pm and plot it as a function of 1 over the temperature T. As a result, we obtain a line whose directional tangent B gives the permanent dipole moment P, and we can calculate the molecular polarization alpha from the intersection A of this line with the ordinate axis. Here such measurements is shown for water vapor, ammonia and hydrogen chloride. If the values of the intercept A and the slope B are determined from the experimental data, then the values of the molecular polarizability alpha and the permanent dipole moment P of the gas molecules can be computed from these formulae. The knowledge of these quantities is crucial for our understanding of the structure of molecules. Besides the molecular polarizability alpha, we also use the polarizability volume alpha prime defined by alpha over 4 pi times the vacuum permittivity epsilon naught, which is interpreted as the volume of a conducting sphere that has the same polarizability as the atom or molecule in question. For example, from the measurements performed for hydrogen chloride, the intercept A in its plot is equal to about 2.6 cubic centimeter per mole, which gives a polarizability volume of 2.6 angstrom cubed for a hydrogen chloride molecule. Similarly, the slope B of the line fitted over the data points of hydrogen chloride is equal to about 650 cubic centimeter Kelvin per mole, which gives a permanent dipole moment of 3.44 times 10 to minus 28 coulomb centimeter. The values of both quantities determined experimentally by applying this method show excellent agreement with the values derived from quantum mechanical computations. Finally, we note that if we take both types of displacement polarizability into account, that is, we also consider ionic polarizability, then we need to write the molecular polarizability alpha in the Clausius-Mossotti-Debye equation as the sum of the molecular polarizability alpha E due to electronic polarizability, and the molecular polarizability alpha I due to ionic polarizability. Then we obtain the most general form of this equation.